Hi all chemistrians, play the best concept video lectures with best analysis, trust equals to success here. Just look at a CSIR June 2011 chemical sciences problems here. Alkali metal superoxides are obtained by the reaction of oxygen with alkali metals in liquid ammonia, water with alkali metals in liquid ammonia, water with alkali metals, and fourth one, hydrogen peroxide with alkali metals in liquid ammonia. Just remember that, or just note down, alkali metals in liquid ammonia is a good source of one electron reducing agents. Okay, right. And whenever metal, that means alkali metals, are taken in liquid ammonia, the reaction products are solvated metal ion and solvated electrons. Okay, we know that ammonia auto ionizes into NH2 minus and NH4 plus. Okay, so that leads to solvated metal ion and solvated electrons. Solvated electron reacts with molecular oxygen to produce superoxide O2 minus. Okay, and that superoxide reacts with solvated metal ion and produces metal superoxide. Okay, here solvated electron produces blue color or impart blue color to the alkali ammonia solution. Okay, right. Here the first option, where oxygen with alkali metals in liquid ammonia produces alkali metal superoxides. Okay, yeah. Next question, hydrogen peroxide reduces. So just check given for a species. So the first one, whenever hydrogen peroxide reacting with iron complex in presence of hydroxide, it simply reducing iron plus 3 to iron plus 2. Okay, whereas hydrogen peroxide directly reacting with KiO4. Okay, and where iodine plus 7 is reduced to iodine plus 5 with that hydrogen peroxide, whereas hydrogen peroxide reacting directly with the cermium sulfate, whereas cermium is in plus 4 and which is reduced to plus 3. And hydrogen peroxide whenever reacting directly with SO3 minus 2 producing SO4 minus 2, where sulfur is oxidized instead of getting reduction. Right, just look at all of them in 4 reactions, the second and third reactions where hydrogen peroxide directly reducing those species. Okay, whereas in the first one hydrogen peroxide can reduce the given iron complex in the presence of hydroxide. So without hydroxide, hydrogen peroxide not going to reduce the given iron plus 3 complex. So we can eliminate first one and also fourth one, because fourth one is where in the fourth reaction hydrogen peroxide is oxidizing sulfur from plus 4 to plus 6. Okay, so second and third, so here B and C are the correct options where those species are reducing by H2O2. Okay, right. Next one, trisodium phosphate. So here trisodium phosphate used as water softener, and by just looking at trisodium, okay, here sodium is present, so whenever we just looking at sodium, okay, so simply which is involving in water softener. Okay, next one, triaryl phosphate. So here triaryl phosphate used as in plasticizer. Next one, triethyl phosphate used in insecticide, used as insecticide, and calcium hydrogen peroxide used in toothpaste. Okay, right. And next question, among the following statements identify the correct ones for complexes of lanthanide plus 3 ions. Here metal-metal bond is significantly ionic, so is it correct or not? So the first statement is the correct statement, because we know that lanthanum plus 3, okay, or lanthanide plus 3 ions are having F orbital, that means inner F orbital, which is highly shielded by 5s and 5p orbitals. That's why here the lanthanide plus 3 ions coordinate with ligands simply with electrostatic forces. Okay, so simply here we can say that metal ligand bond is significantly ionic in nature. Okay, not covalent type, because just due to 4f orbitals are buried in lanthanide ions, that's why they can interact electrostatically, or they can interact with ligands by electrostatic forces only. So we consider lanthanide metal ligand bond significantly ionic in nature. Second one, complexes rarely show isomerism. Yes, so this is also the correct statement, because the lanthanide ion size is more, that means large size, and lanthanide ions are having mostly basic in nature. Okay, and unavailability of orbital, as we said, 4f orbitals are buried in the that means for that particular lanthanide plus 3 ions. Okay, so all these circumstances simply leads to make few complexes with ligands, okay, by that particular lanthanide plus 3 ions, and that's why the isomerism is also rarely shown by lanthanide metal complexes. Okay, because they can make few complexes with just like oxygens, mostly with lanthanide makes complexes with oxygens, and also we can see some more ligands like nitrogen ligands. Okay, right. And here the next statement, the coordination number is not more than 8. So this is wrong statement, because we can see cermium which is coordinating with 6 ligands of nitrate. So where NO3 here is acting as a bidentate ligand, that's why cermium is having 12 coordination. So more than 8 coordination is also possible for lanthanide plus 3 ions. So third statement is wrong one. Now just come to the fourth one, the magnetic moments are not accounted even approximately by spin only value for majority of lanthanides. Okay, so here what is saying, the magnetic moments are not accounted even approximately by spin only value for majority of lanthanides. Okay, so here this is also a correct statement, because spin only formula is not enough to find magnetic moments of lanthanide complexes or lanthanide ions, because here you can see the 4f orbital is buried, and which contains electrons, and here different distribution of electrons are observed on 4f, that means on f orbital. So the orbital contribution is also there for magnetic moment calculations. Okay, so that's why here to calculate magnetic moments of lanthanide ions, we need to consider spin and orbital contribution. Okay, so that's why here fourth statement is also the correct statement. Okay, next one, according to Vesper theory, the molecule or ion having ideal tetrahedral shape is, so here we have a method, that is here we have given it SF4 species, where sulfur is central atom, and which is having 6 valency electrons, and 4 electrons are making sigma bonds with 4 fluorines, and 2 electrons are simply considered as one lone pair. Now the hybridization is sp3d with one lone pair, and we can say it as seesaw form, okay, or seesaw shape. Now for SO4 minus 2, so just use same thing, and we can get sp3 hybridization, okay, with which is tetrahedral in nature, because no unpaired electrons are observed for it. And next one, SO2Cl2, where sulfur is a central atom with 6 electrons, and just 2 electrons making 2 sigma bonds, and 2 oxygens are making 2 sigma and 2 pi bonds. So here sp3 hybridization, and without lone pair of electrons, but different bondings Okay, so you can see sigma bonds with two chlorines and sigma and pi bonds with oxygens. Distorted tetrahedral structure is observed for this species. Okay, whenever all the groups or atoms are same, then it is completely tetrahedral, but here the groups are different. Okay, atoms are different, so we can say it is distorted tetrahedral due to the repulsions can be observed between these oxygens and chlorines. Okay, bond deviations, bond angle deviations can be observed. That's why distorted tetrahedral structure is for SO2Cl2. Now just come to S2Cl2, where we can expect one sulfur-sulfur bond. That's why the electron contribution is there for making sulfur-sulfur bond, and two chlorines, one electron of sulfur making a bond with chlorine, and for other sulfur making a bond with chlorine. Now, so we have 6 electrons on each sulfur. So one electron is for sulfur-sulfur bond, and other electron is for making a sigma bond with chlorine. Now 4 electrons are just remained each on sulfur. Okay, that's why here we can say sp3 with 2 lone pairs on each of the sulfur. So sp3 hybridization with 2 lone pairs considered as bent structure. So on each sulfur you can observe bent like shape. Okay, right. And next one, the complex, here we have given it manganese complex, has very light pink color. The best reason for it is the complex doesn't have a charge transfer transition, DD transitions here, or orbital forbidden but spin allowed, DD transitions here, or orbital allowed but spin forbidden, DD transition here, or both orbital forbidden and spin forbidden. Okay, right. Just to look at the accretion state of manganese, that is in +2, so it contains 5 d electrons. In the presence of ligand water, the d generate d orbital splits into T2G and Eg because it is octahedral complex. Right, 5 electrons can feel just like this because water is a weak field ligand. That means high spin you can observe here. Okay, right. Now after drawing this, so we need to look at the selection rules. Right, first we need to look for the spin selection rule. Right, so we know that spin selection rule, the spin must not be changed during the transition from one energy level to another energy level. For example, if electron is transferring with plus sign, plus half, that should be transferred just like plus half. Okay, so then only it is spin allowed. Right, but here from T to G, the plus half if moves or transfers onto Eg, then spin must change. Okay, that means the sign must change, then only the electron pair up. Okay, so that's why spin forbidden. Now we need to look for the orbital contribution, or simply we can say Laporte selection rule. We need to look at Laporte selection rules. So according to Laporte selection rules, the parity must be changed in transitions from one level to other energy level. Okay, right, parity means Garrett to ungarrett or ungarrett to garrett. Okay, so just remember that Garrett to ungarrett is a low transition, ungarrett to garrett a low transition, whereas garrett to garrett or ungarrett to ungarrett forbidden transitions. Okay, right, and just remember that for octahedral complexes G is present. Right, so you can see garrett and garrett. So for octahedral complexes G is present just because octahedral complexes contain center of symmetry, whereas Laporte selection rules are not applied for tetrahedral complexes because they lack of center of symmetry. Okay, right, and here so you can see Garrett to garrett transition you can observe. That's why orbital forbidden, that means Laporte forbidden. Okay, so that's why here spin forbidden and Laporte forbidden. So here both that means spin and Laporte forbidden. So absorption associated with doubly forbidden transitions are extremely weak and show light color. Okay, So that is the just check the correct answer from the given options. Okay, yeah, so here the given complex is showing light pink color, that is just due to the doubly forbidden transition. Okay, yeah, next one, the highest order of ligand to metal charge transfer energies. So here just understand the information given in the problem. Here highest order of ligand to metal charge transfer energy, that means whenever charge transferring from ligand to metal, so we need to check the order where in an increasing order of energies. Okay, right, in that case so the first one MnO4, where manganese in +7 oxidation state, chromium is in +6 and vanadium is in +5 with same ligand. Okay, right, and we know that whenever oxidation state is more on metal complex, then ligand to metal charge transfer is very easy. That's why the energy is less needed for it. Okay, whenever charge increasing on it, then electron density increasing around that metal, in that case from ligand to metal charge transfer is difficult, because metal is getting satisfaction with electron density on it. So that's why it doesn't need to get a charge transfer from ligand to metal. In that case, to transfer charge from that ligand to metal, so more, that means high energy is needed. So in that case, now vanadium with +5 oxidation state, that's why in most energy, that means highest energy is needed to transfer charge from ligand to metal on vanadium. Okay, so what is the correct order from, so just like this is the correct order of increasing energies to transfer charge from ligand to metal. Okay, next one, the highest occupied molecular orbital in N2O2 plus respectively are. Take x-axis as internuclear axis, right? So this is the key point. Okay, that is x-axis as internuclear axis. Okay, so now we need to draw molecular orbital diagrams, and for N2, which is having 14 electrons, so just to fill the 14 electrons here. Okay, and in that case just try to fill. Now whenever we fill the two, that means electrons, highly occupied electrons will be in 2px, so that is sigma 2px. Okay, right, and whenever we come to that O2 plus, where the highest occupied electron is moving on to pi 2py, that is pi star 2py. So first option is the correct answer for the given problem, right? And just look at here that, sorry, here just wrong molecular orbital drawing. For 14 electrons of N2, the 2px must be above. Okay, so just change that, sorry for that. And here, so 2 electrons filled here and 2 electrons are filled here and 2px. Okay, so 2px is above that 2py and 2pz, and 2px is internuclear axis for both N2 and O2 plus. Here 14 electrons to be filled. Okay, so just draw the lowest energy as 2py and 2pz, and the highest energy is 2px, and which is internuclear axis and which is making sigma bond, okay, in between two nitrogens, right? And here we have 15 electrons, and the 15th electron is just moving on to 5 star 2py. Okay, so just correct this, so sorry for the just wrong drawing. And from this we can simply say that sigma 2px and 5 star 2py as a correct answer. Next one, carboxypeptidase contains zinc +2 and hydrolyzes carbon dioxide, and zinc +2 hydrolyzes peptide bonds simply by just observing carboxypeptidase. So here peptide bonds are getting hydrolysis, and here zinc +2 is the active site in it. So second option is the correct answer. In the EPR spectrum of tetragonal copper +2 complex, when So G parallel is greater than G perpendicular is greater than G electron. The unpaired electron resides in the orbital. So here we have given with copper plus 2 complex, where copper plus 2 is containing 9 electrons in its d orbital. So in the presence of ligand, field splits into Eg and D2G and further splits into dxz, dyz, dxy, dz square, dx square, y square, and dx square y square is having highest energy orbital. Okay, so why dx square y square is the highest energy orbital? So that means the unpaired electron is present in dx square y square. How can you say that? By just looking at G factor, that is Landis splitting factor or spectroscopic factor. Okay, here G is a function of electronic environment. Okay, G indicate electron environment. So that's why here just remember the G parallel indicating GZ, that means electron environment or electron density around or just parallel to applied magnetic field, and G perpendicular indicating Gx and Gy perpendicular to applied magnetic field. Okay, right, and by just observing this, so G parallel is greater than G perpendicular. So that means electron density is more along the Z axis. That means simply we can say dz square has highest electron density. That's why 2 electrons must be filled in dz square. Whenever 2 electrons must be filled in dz square, 1 electron should be occupied in dx square and y square. Okay, so this analysis is enough to find the correct answer for a given problem where the 1 electron is in dx square y square. For example, if G perpendicular is greater than G parallel, that means electron density or electron environment is more around dx square and y square. In that case, dx square y square should have 2 electrons and dz square should have 1 electron. Okay, right. And next one, the oxidative addition and reductive elimination steps are favored by. So here for oxidative addition, that means what is oxidative addition? So the name itself is saying that the oxidation of metal should be takes place. Okay, so to get the oxidation of metal should have more electrons. That means the metal should be electron rich. Okay, for that oxidative addition. Now just come to reductive elimination. So the metal should get a reduction. In that case, metal should be electron deficient. Then only reductive elimination is possible. Electrons can add onto the metal. Okay, so from this we can say that oxidative addition involves electron rich, and for reductive elimination, electron deficient metal centers. Next one, identify the order according to increasing stability of the following organometallic compounds. So here just look at all the given 4 species or 4 complexes where tetraisopropyl titanium, you can observe that here alpha and here beta, and you can see at beta carbons where methyl groups are there, that means hydrogens are present. So beta hydride elimination is very common, and which is here more possibility is there on tetraisopropyl titanium. In that case, so it is most unstable complex here. Okay, organometallic complex or compound here. Now just come to tetrabenzyl titanium, where we have alpha hydrogens but there is no beta hydrogens. Okay, alpha and beta, so no beta hydrogens. In that case, no beta hydride elimination. That's why which is the most stable organometallic compound in the given species. Okay, so from left to right, the stability increasing due to decreasing beta hydride elimination. Okay, right. Next question, among the metals manganese, iron, cobalt and nickel, those would react in its native form directly with CO, giving metal carbonyl compounds are. So simply nickel reacts directly with carbonyl. So okay, CO here at 1 atmospheric pressure 25 degrees centigrade produces metal carbonyl, whereas iron directly reacting with CO and at 200 atmospheric pressure 200 degrees centigrade produces iron carbonyl. Okay, next one, the molecules with highest number of lone pairs and has a linear shape based on Vesper theory is. So here just use the same method. The carbon dioxide central atom is carbon, and which is making bonds with oxygens. So here sp, so sp without any lone pair of electrons, simply linear in nature. So whereas if you look at for oxygen, 2 electrons are sharing to make sigma bonds with carbon, then other 4 electrons are remaining on each of the oxygen. So you can say that total of total of lone pairs equals to 4 on that carbon dioxide. Now by just using same method, I3 minus is linear, where each iodine with 3 lone pair of electrons, so total 9 on it, and for NO3 minus 6 and for NO3 plus 4. So the highest number of lone pair of electrons present on I3 minus. Okay, yeah. Next one, given silver plus and electron, sorry, here just read it as just the half cell here, silver plus electron producing silver with reduction potential 0.50 volt, and the copper half cell with reduction potential value 0.34 volt. A 100 ml solution is 1080 milligram with respect to silver plus and 635 milligram with respect to copper plus 2. If 0.1 milligram silver plus left in the solution is considered to be the complete deposition of silver plus the cathode potential, so that no copper is deposited during the process is. Okay, right. For the copper half cell, reduction potential is given 0.34 volts. Now we need to use the formula, that is E cell is equal to E0 cell minus 0.0529 by 2 log 1 by copper plus 2 concentration. Then next equation here we are using, and just substitute E0 cell value of that copper half cell, and 2 electrons are involving, that's why n is equal to here. Okay, and now the concentration of copper plus 2, that is molarity of copper plus 2 is just calculated or just taken as 635 milligrams. Whenever we convert into grams, that is 635 into 10 power minus 3. So grams by molecular weight of copper plus 2, 63.5 grams per mole into the volume. So that means simply here 100 ml solution, which is considered as 0.1 liter. Okay, so just substitute all of them, and from that E cell of that copper half cell is 0.31 volt. Now for silver plus, and that is the answer, option 3 is the correct. For silver plus half cell, the silver half cell, now just use the same equation and substitute their values, where silver plus concentration we have given with 0.1 milligram. So whenever we convert it into grams, 0.1 into 10 power minus 3 grams by what is the molecular weight of silver, 108, and here 100 ml, that is whenever convert into liters, it is 0.1. Okay, so gram by molecular weight into volume result concentration of the silver plus, and just substitute it, and we can get 0.203 volts. Okay, right. Thank you very much.